Hello, pre-matriculants. I hope you're up
Not
and ready now.
matriculants.
It's pre-matriculants.
Pre-matriculants.
That's what I
I'm
just
sorry.
said. That's
Hey,
what I just said,
you're
John.
too sharp today.
You
Sorry,
know what? John
Abram.
is up and ready.
Yeah,
He
I'm
just
wanting to
can't
jump
wait.
in. Hey, yeah.
I see.
Yeah.
Okay, once more again, good afternoon to you all pre-matriculants. Hope you're up and ready to learn more with us. As you can see, John is up and ready. I cannot say anything. John, how's you?
I'm really good, thank you. Great to see you again, grade 11s. Now, last night I just did a little bit of a thing with some of the people watching maths, but today I've got the whole show, so we're going to do the whole thing. So let's get going.
Right, talking about what we're doing today. What's on the menu?
It's electromagnetism. So it's the connection between electricity and magnetism. Now, you might have played with some magnets. We all know about electricity, the lights and what have you. Now we're going to see how they work together, how we can put those two ideas of electricity and magnetism together. Isn't that cool?
It's so cool. You know what? 2 words to describe the show. It's just fun and learn.
Absolutely.
That's all. I'm looking forward. Well, my mindset is to join us on this fun and learning show. Make sure that you go over Facebook. Our Facebook page is facebook.com/LearnExtra. Secondly, follow us on Twitter @LearnExtra. And lastly, you can download the notes. They're already posted on our Facebook page, all for free on learnextra.co.za/live. And let's learn, have fun also.
Abram, thank you so much. Right, now guys, let's get going. So, electromagnetism. So what are we going to do today? There are a couple of things we're going to look at. The first thing that we're going to look at is we're going to discuss the magnetic effect. So let's just get the pen right. The magnetic effect of an electric current. So we're going to look at what happens when current passes through a current carrying conductor. And we'll be surprised, or we shouldn't be surprised because you've seen it before, that there's a way of, if you allow current to pass through a current carrying conductor, it produces a magnetic field. But then the exciting bit is that we're going to go the other way. So we're not only going to say, well, if a current produces a magnetic field, we're going to say, what can we do with a magnetic field to produce a current? And that's revolutionary. It actually transformed the whole of human history. We would not be in the position where we are today if it wasn't for this understanding that you can take a magnetic field and you can make current from it. Because if we were just dependent on batteries, we'd have a whole lot of lemons and metal stuck into them and have cells like that. We wouldn't have all the electrical appliances that we've got. We wouldn't have dynamos and motors and generators, and I know the grade 12s are going to be learning about that a little later as well. So guys, this is important. This is foundational stuff. You need to appreciate and understand that you can both produce a magnetic field from a current, but you can use a magnetic field to make a current, to make a potential difference. And we talk about that as electromagnetic induction. And the amazing man that discovered all about this process is called Faraday. Michael Faraday. He's one of my heroes. Abram, did you know that Michael Faraday, although he lived a long time ago, has got so many things that we can learn from him. He didn't have a formal education, so he was basically kicked out of the house because his mom and dad couldn't look after him at the age of 11.
Sure.
Between 9 and 11, okay? And he had to start working. So he was an unemployed youth, okay? And he went and he got a job as a bookbinder. At that stage, he hadn't been to school.
Wow.
He taught himself to read and write.
Wow, very interesting.
Okay, so here's a guy that came from absolute poverty.
If I may ask, is the Faraday taxi rank named after him?
Might be. He's a very famous guy, and his fame has spread all over the world. So Michael Faraday comes from a poor background. He couldn't read or write even up to the age of 11 or 12, didn't go to school, taught himself to read or write, became a lab assistant. In those years, okay, 1780, 1790, somewhere around there, what happened is that only the people that were from royalty could go to university. Only they could be scientists, the nobility. So if you weren't born into noble, you couldn't study science. And you know what? The other interesting about Michael Faraday is he popularized science. He started to explain principles of science to ordinary people. Isn't that amazing?
So amazing.
So I mean, he's got lots of inspiration. Guys, I'd like you to do something, just as a fun exercise. See if you can find out about Michael Faraday. And perhaps even post them on the page.
I'm on it too.
Okay,
you know what?
great.
I'm so inspired.
Let's yeah, he's an inspiring man. He's actually got so many things that he found out and he invented, and we can just be grateful to Michael Faraday for not keeping all his knowledge to himself, but by sharing it and making us excited about science.
But we're saying to the mindsetters they should read.
Yeah, read, find out about it. See, and you know what? He never gave up. Even though he didn't let his background be an excuse for determining where he would get to. And he actually became a very famous scientist just because he was determined. And so the same applies to you. You don't think that because you were born in a poor background from a poor family, you don't go to a good school, that you can't achieve. You can achieve if you stick at it. So that's my inspirational bit for today. Let's get on with the science.
I'm pumped up already.
Okay, right, guys. Now, let's get going. So what's this thing called the magnetic field? Now, I'm going to take you back to some stuff that I'm sure you've done in primary school. Do you remember when you dealt with magnets? So I'm just going to extend this page a little bit. And I'm going to just do a little drawing here. And hopefully we can get something colored in it. So there we go. We've got a little block over here. And we're going to say, let's make that side the north, and let's make that side the south. And we've got a little magnet, a bar magnet. Now, what do we know happens around a bar magnet? Well, in the space around the bar magnet, if I bring anything that is magnetic into that space around here, it will be influenced by the bar magnet. Okay? So it will be either attracted or it will be repelled. Depends on its magnetic properties. So if I bring another magnet, and one of the examples that we use when we do this sort of thing is we take a little compass needle. A little compass needle has a magnet stuck on a pin, and it's able to move. So it's free moving. Okay? And what we're going to say is that the north pole of that free-moving little compass needle gets repelled by the north pole of the magnet there. And so we could move this little plotting compass around the area, the region in space, and it would form little lines. And these little lines that I've drawn here are the beginnings of what we call a magnetic field. So it's actually a region in space which will be influenced by anything magnetic. One of the things that I'm drawing here is just to show you that these field lines that we draw never cross. They always stay next to each other. They stay parallel to each other. And another important principle, and I'm just sketching them here, so please don't get me wrong, is where there are lots of them. So I'm going to just use the green thing, green box here. Notice there are lots of lines cutting through that green box. We say this is a pole. This is a north pole. And we recognize a pole is a region where there is a strong magnetic field. This is very strong. Strong field. Okay? Whereas where they're further apart from each other, so over here, where we've got this sort of situation here, you'll notice that there are only a few lines cutting through there. It's only two, one dotted and one full. This is a weak magnetic field because the field lines, weak field. Okay? Just remember that this is a region in space. And even though I've drawn it on the flat board, what you need to understand is it's actually also coming out of the board. If this was a real magnet, a magnet would be in 3 dimensions. So it would be out of the board this way, it would be on top of the board, and it would be behind the board as well. All around it, there's this region in space which influences other things that are magnetic. Little compass needle, iron filings, things that have magnetic properties will be influenced, either attracted or move in some way or repelled by the magnetic field. Okay, you got that. Let's just check that I've covered all those points that are in your notes, and I want to just make sure that we understand it. So, let's go through them quickly. Magnetic field is the area in which a magnetic object experiences a magnetic force. I said repulsion or attraction. The correct, another word for repulsion, attraction, is a magnetic force. Now remember that when we're talking about a repulsion and attraction, we know that unlike poles will attract each other. So a north pole will attract a south pole, but a north pole will repel a north pole, and a south pole will repel a south pole. So like poles will repel each other, unlike poles will attract each other. You need to know that. Now, that's all about magnets. Now, what about this thing about current? Now, when we've got a moving charge inside a conductor, okay, then we've got a current moving, passing through a conductor, it creates a magnetic field. So, moving charge inside a conductor, the charge flows down the conductor, it creates a magnetic field. That's amazing. And this was discovered by a man called Ørsted. He was a Norwegian, some Scandinavian guy, I think. He first discovered it in either Oslo or Stockholm. Can't just remember it off the top of my head right now. But Ørsted had this little contraption, and he had a little compass needle, almost by accident. Yeah? And he turned on a circuit, and he noticed, whoop, whoop, the compass needle just deflected. Thought, hey, why is this happening? I've got a little compass needle here, a little conductor, and it's moving. It's just deflecting. What could be causing it? That's the curiosity of science. That's the amazing thing. He didn't just stop there and ignore it. He thought, what must be happening here? And so he began to do some more testing. Eventually discovered that around every current carrying conductor there is a magnetic field. The direction of the magnetic field is defined as the direction in the north pole of a compass will change. Now let's just go to a diagram to try and show this. So here I've got a current carrying conductor. I hope you can see it. It's this one here. So I don't want to change that color because it's too much like the magnetic fields that have been drawn. So if we pretend that's the current carrying conductor there, there's the conductor, there's my conductor. Now, what did Ørsted find? He found, pretend for a minute, my pen is like a current carrying conductor. It's not, because it's not in a closed circuit. What he said is around it, in a circle region around it, like that, like my close of my fingers, there is a magnetic field. And so just like he's showing it there in those, or we're showing it there in these diagrams as concentric circles at different points along the length of the conductor. It's not just at the end, it's not just at the middle, it's down the whole of the conductor. There is a magnetic field. Now you've got to get this right. You've got to be able to recognize it. So if I draw it like this, then I understand. All the way down, there's a current carrying conductor. Notice that it is at 90 degrees or perpendicular to the current. So the red arrow here indicates, and I'm not going to use red, I'm just going to use pink to go over it, that is at 90 degrees to the field. So if the current is going down that way, down the pen, the magnetic field's at 90 degrees like that. Can you see that? Like that. It's at 90 degrees all the way down in a series of these magnetic fields. Now what you'll notice is that the way they've drawn them here, close to the conductor, they're close together. As they get further apart, they do actually get weaker. So they get further and further apart. So around the magnetic conductor, we recognize that they are strongest when they are close to the conductor. The direction of the field is given by the compass needle, where it points. So if we have a conductor, we can see the compass needle, but there's another way of doing it. What we recognize, if the current is changed, if the direction of the current is changed, and remember when we're talking about current here, we're talking about conventional current, from positive to negative. So conventional current from positive to negative, if it's reversed, that means that if we made this one positive now and that one negative, the direction of the magnetic field would change as well. So guys, how are we going to know what that is? So I just want to do a quick thing about that, just to remember that the magnetic field is continuous. It's represented by magnetic field lines, and notice it's three-dimensional, and we've said that already. So how do we work it out? I want to just draw it because I love looking at things and drawing them. Okay, so very quickly, if we've got a magnetic conductor, a current-carrying conductor. Now, my drawing, to get this thing with 90 degrees, I battle. I really do battle. So you know what I'm going to do? I'm going to take an end view. I'm not going to take a sideways view as I've got here. I'm going to say, what does it look like if I was looking at the current carrying conductor from the end? Is that fair enough? So here's the challenge, guys. If I had to take the side, not the side view, I take the end view. And we'll just write it down here very quickly. I know we're almost out of time, but I want to just draw this one thing. And I'm going to say, there's my conductor. Now, what I need you to understand is I'm going to do another one of those. I want a second current carrying conductor. So I'm going to put it over here like this. Now, when we're dealing with this section of physics, what we need to do is have a symbol to represent when things go into the board and out of the board. So, into the board, what shall we do? Well, what they've decided is we'll make that a cross. So we'll make that a cross. And coming out of the board, we'll make it a dot. It's a bit like throwing a dart. I don't know if you've thrown darts to a board or shot arrows with a bow and arrow. There's a fin at the back. That's it going in, the back of the thing. The point, hey, the dot is coming towards me. Hey, I must watch out. So now how do we tell what's the magnetic field here? Now, the easy way to do it is you use your right hand. Guys, the right hand rule. What we say is the thumb points in the direction of the current, and the curl of your fingers shows the direction of the magnetic field. We draw the magnetic field as concentric circles. That's one circle, and then a bigger circle, and then a bigger circle. Right, I want you to take a look at those two pictures, and I want you to draw, use the right-hand rule, to draw the magnetic field around them. And we'll check them after the break. Abram?
Thank you so much, John. You know what? I'm just watching and learning a lot because I'm enjoying the lesson, especially when you speak about darts, because I'm a former darts player.
Hey, excellent. Yeah.
So
you know what? Yeah, you know what I'm saying, eh?
Yes,
Okay.
I get it very well. And did you know that there's a famous quote that Mr. Faraday once said? He said, "A secret is compressed in 3 words: work, finish, and publish."
Excellent.
I like that.
Like it too. Okay, let's go for a break.
Right. See you after the break, Mindsetters. Welcome back, Mindsetters. Now, on the page, there are some exciting comments that I need to read out to our teacher just before we get, to the action. Vincent River says, "Ish, long time no see. Where have you been, John?"
Hey, Vincent, how's it?
And another one, it's from Neo saying, "My favorite teacher and my favorite subject and my favorite teacher. Highlight you, Mr. John."
Cool. We'll chat to you on the page as well. Hey?
Right one.
Sometimes people have to do work in the background. I'm one of those. I don't always get on, but I'm always there watching what's going on, and I wish you all the best.
Overall,
Thanks for
the
watching.
Mindsetters are enjoying the show, and let's learn more.
Let's go. Guys, have you got the answer? Hey, I'm not worried about the fun and games. Have you got the answer? Have you done your sketch? Remember what I asked you to do during the break? If you take a drawing like that, remember what that means. That's saying that we've got a current carrying conductor, and the current is going in which direction, Abram, the darts player? Current is which, in or out?
Out.
Hey, come
No.
on.
In.
Which way do you throw the dart? Did you, and what do you see when you throw the dart?
You see
The tail.
The tail, yes.
Yeah, so it's going in.
In. All right.
Okay.
I see now.
Okay. So did you ever stand on the at the front of the board and let other guys throw at you?
No,
No, you
never.
wouldn't do that. But if you did, what would you see? You would just see the point. So here, the current is going out with that.
Mm-hmm.
So over here, it's going in because we see the cross. Cross means in, okay? Point means out. Got it. Now, we've got to show the direction of the magnetic field. Is it clockwise or is it anti-clockwise? How are we going to work out? Remember, if you did this experimentally, you would have your piece of wire pointing down, you'd put a little compass needle around, you'd see which direction the compass pointed in. But here, I've said to you the way we're going to do it is we're going to use the right-hand rule. Not the left hand, the right-hand rule. We're going to point the direction of the current with our thumb, and we're going to use the curl of our fingers to show the direction of the magnetic field. But let me get some field lines out. So I've changed the color of this circle here, and we try and get it as circular as we can. Let me just move that one a little bit. So it's more or less circular. Forgive me if it's not totally circular. We're just going to draw another one. And I'll draw one more as well, but let's just get that one as big as we can. Oh, this one I'm going to delete. Sorry, guys, because I don't want to have too many. We're going to take that one, make it big. Come on. There we go. Now, you can see concentric circles. They all should be circular. This one is playing up this. There we go. Almost a circle. But I think that's pretty good. Okay. So it's almost, we would draw them with a compass, and we would draw them nice and circular, just making them bigger and bigger and bigger. But for a sketch, that isn't too bad. Now, what we've got to do is we've got to indicate the direction. The direction of the current is given by the right-hand rule. So in this case, I'm going to put the thumb pointing in. Notice my thumb is in that direction. It's going in, and I turn my fingers in this direction. It's right hand, check. I know that I write with my left hand, so it must be the other hand that I must use. So my thumb goes in, and the curl of my fingers tells me that this is in a clockwise direction. It's in that direction. And I can put the arrows on those circles to show that if I put a compass needle, this is the important thing. If I put a little compass at this point over here, the north would be indicated in that direction. North would be pointing in that direction. And that's why we show the arrows. The arrows indicate the direction of the North Pole. Okay, so be aware of that. Now, if that was the field direction going in, look what's going to happen. I'm going to turn around. It's now the current is coming out, and I'm using my right hand. The thumb is now pointing towards you. The curl of my fingers is the other way around, and I'm just going to quickly put some lines in over here. And in fact, I'm just going to do one so that we don't waste too much time, and indicate that magnetic field as coming in the which direction? Anti-clockwise direction. So guys, this is anti-clockwise. It's coming around like that. Now, you need to know the right-hand rule. You need to be able to use it. This is the right-hand rule for a straight current carrying conductor. Okay? Remember what we said. There are many field lines. There's one current. So the thumb is the one thing. It's the current. The many fingers are the field lines. It's the curl of the fingers. Got it. Right, let's move on. Now, the next slide just simply indicates that. So we're going to skip that on. It's in your notes so that you've got it. There's no confusion. In fact, there's one other thing I want to do. Just quickly, let me go back, because there's one little thing that I want to prepare you for. Guys, listen to this very carefully. If you want to see the pretty pictures, you need to go to the Mindset lesson on the website. I'm going to tell Abram what that lesson is, and you go and have a look at it. See if you can watch it online, or you can order the DVD. But it's on electromagnetism on the main website under Classroom Resources. Go and have a look at it. It shows these beautifully. I'm just going to try and sketch them. Remember what I said to you. This picture was the top view. What I'd like to say is, what happens if I look at it as a side view? What would it look like if I looked at it from a side view? So I'm just going to draw in one direction now. So I'm going to say, there's my current carrying conductor, and I'm going to say, let's pretend the current is in that direction. Abram, help me out here.
Yes.
What did we say? How are we going to determine the direction of the magnetic field? What do we use? What hand do we use?
Right hand.
And what direction does the thumb point in?
It's
current.
It's current.
Yeah. And so if that's the current, I'm just going to remind you that that's I. So the current is going up. Okay. So now I put my thumb over there, current going up. What do you notice about the curl of my fingers now? It's a bit funny, hey?
Yeah.
Now, you're a graphics artist.
Yes.
Okay, you're a darts player, a graphics artist, a radio presenter, all sorts of things. Hey, this man's man of many talents, eh? So you've got to recognize some talent. Now, Abram, I'm not a 3D drawer. Eh? I don't know if you battle with 3D. Sometimes I battle.
No,
you manage it, fine. But you know what? Normal people, the scientists around, we want to draw it quickly. So we don't have time to give it to Abram to draw all the time. Okay? So we want to draw those rings. Okay? But, hey, it's tough, man. I can't draw in 3D. So we got a symbol. Now, the darts player. Tell me something. Abram, what did we say about our definition for something that is coming out? What was that?
Something that is coming out.
Coming towards you. What's the dart going to look like?
It's
a dot or a cross?
Well, it's a dot.
It's a dot.
Yes.
So, guys, I want you to imagine that's the side view, and we're going to take a slice around all those rings. Now, remember, they can be going clockwise or anti-clockwise. In this case, if I was to look from the top, I'm recognizing they're going anti-clockwise, so they're going like this. So they're coming out on this side and going in on that side. So out on this side. So out means what? Dot or cross?
Out is a dot.
A dot. So I'm going to put some dots over here. Guys, now notice something. There's a dot, there's a dot, there's a dot. So all the way around, the whole length of the conductor, there are dots, saying the magnetic field is coming in which direction? Out. Okay? On this side, magnetic field is going in. You got it? Now, the thing that I want to stress here is notice that these magnetic field lines are close to each other because they're close to the conductor. They're many. As I get further apart, further away, I won't have so many magnetic fields. And so somewhere out here, I might only have just a single little magnetic field because it's tapering off. The further I get away, the weaker the magnetic field. Remember, when they're close, lots together, strong. Far away, weaker, weaker, weaker. Now, you know this. If you take a magnet, you can't stand 20 meters away and get pulled by the magnetic field. No, not even if you're Iron Man. Clunk! No, that doesn't happen in real life. But if you're close to a very strong magnet and you've got a piece of metal, it will jump. So recognize the magnetic field spreads out over an area. This magnetic field is cutting perpendicular to the movement of current. Now, guys, this principle is going to be very important when we get to Faraday's law. So I want you to remember this picture. You can go and draw it the other way when the current's the other way, but all that we'll find is there are crosses on that side and there are dots on this side. So let's move on. I'm going to skip forward, and I'm going to say, right, now, very important idea. scientists didn't just like to have long, straight conductors, they turned them into a coil. And when you turn a conductor into a coil, you get what we call a coil, circular coil, not difficult to see that, but it's also called a solenoid. Okay. When we do this, we can find that we've got an electromagnet. Now, I'm sure even in primary school, you might have done this. Taken some copper wire, wound it around a couple of nails, connected it to a battery, used the nails to pick up other things. You've made an electromagnet. You turn off the battery to open the switch. It's no longer a permanent magnet. So we can use this idea of a circular coil to create a magnetic, a temporary magnet, an electromagnet. Remember, the word is electromagnetism. So this is the first aspect. We're taking current and making a magnetic field. This is very useful. You know what? You have electromagnets all around the place. You have electromagnets in your loudspeakers, in your computers. You have electromagnets that are writing on your discs. You have electromagnets that are putting up switches. So electromagnets are really useful, and they're very important. So we must remember them. So what do we recognize? There is something very special about the electromagnet. If you've got lots of coils, you make a stronger electromagnet. Now, there is another right-hand rule. Now, I hope you can see the direction of the current is indicated by those arrows. So this is rotating in that direction. And what we're going to say normally this is just a single coil, but normally we would have lots of coils together, lots of wrappings of wire around. We're making a magnet, an electromagnet. The right-hand solenoid rule works here. Now, because you've got lots of coils, we're now going to say, let's use the many fingers, many coils, to show the direction of the North Pole. Because this coil arrangement, the solenoid, becomes a replacement for that permanent magnet with the north and south end. So look what happens. We take the many fingers and we curl them, and the thumb is now pointing away. Can you see? Right hand, my thumb is pointing away from you. Curl of the fingers, that direction, the thumb is pointing away. That means that this end of the coil is south. The other end, if I looked on the other side of the board and I went around the back there, and I looked at it, that end of the magnet would be the north side of the magnet. Okay. The magnetic field around a coil is just like the one we drew of a permanent magnet. Right, let's move on. Next page. And that's what we've shown there. So that when a current is passed through a solenoid, many coils, an electromagnet, the electromagnet is just like the bar magnet. Moving on. There are three things that you can do to strengthen an electromagnet. You can increase the number of coils, you can increase the current, and you can replace the metal inside. And if you make it a soft iron core and make it bigger, then you've got more magnetic field lines passing through that. The little domains inside the soft iron will line up, and they'll become magnetic temporarily. So those are the three things of increasing the strength of the magnetic field around a solenoid. Please make sure you learn that. It's a question that is often asked in the exams. Abram, are there any questions?
So far, the mindsetters have answered the question. There's a question that was saying, is it necessary to use the right-hand rule? Instead of knowing incoming current, the current will flow in clockwise direction, and outcoming current goes anti-clockwise direction.
Look, you can learn it like that. I just like to have a hand rule, a memory thing, because in the exam, you know what, I could just forget it. But I know the right-hand rule. And I know that that always works. And I'm not going to get confused. It just helps me with my deciding. Okay.
So it's more for you not to make some mistakes.
Yeah, it's recognized as a rule that we use in determining the current. Okay.
All right, as we're about to take a break, here's a quote from Mr. Faraday from a Mindset Abafana household, Matlango. He says, "There is no more open door by which you can enter into the study of natural philosophy than by considering the physical phenomena of a candle." I like that one. Thank you so much, Bafana, and do not move, Mindsetters. See you after the break. Welcome back, Mindsetters. Now, exciting news that I need to tell you. From the 25th to the 27th, on Saturday, we'll be having a feature-ed and education show happening at Coca-Cola Dome in Johannesburg. So make sure that you do come through, whether it's Thursday or Friday or Saturday, to meet us as your presenters and also to help you understand more about mindset. So, John, let's take it away.
Thanks, Abram. Guys, Future Ed, don't miss it. If you're in Gauteng, be there. Don't miss it.
You can register for free.
Yeah, it's free. You can get in. There are lots of giveaways. There are competitions. Hey, we're running a really cool one. So make sure you're there. Put your name in the box. There's a lucky draw every day at 3 o'clock. Make sure you get in. And you could be a really lucky winner. There's lots of stuff that's happening at Future Ed. I'll be there on Saturday. So hope I'll see you. Right, guys, let's get going. Here we go. The first part, and I know we ran over a little bit of time, the last two sections, we've been dealing with current produces magnetic field. And we've set some things up. Okay? Talked about what a magnetic field is. Now we're going to go the other way. And this was the debate that lots of people had. You know what? They thought it was going to happen, but they couldn't quite get it right. They thought if they got a big enough magnet, it would produce a current. Hey, they got big magnets, they made big electromagnets, and they tried to measure current around them. And there was nothing. They turned the wires this way, they turned the wires that way, they made coils around. Nothing happened. And then Michael Faraday one day, he was setting up part of the equipment, and he suddenly just moved one of the coils. Oh, there the needle deflected. And so what he found out was just like you need a moving charge to create a magnetic field, you need a moving magnetic field to create a current, to make the charge move. So, very important idea. There has to be relative motion. And this little animation here on the board describes Faraday's law quite nicely. So, what we've got is we've got a coil. Now, notice the potential difference before the magnet moves in is 0. The magnet with the north pole moving in, and it deflects to one side. When it comes out, the red needle deflects to the other side. So, watch this very carefully. Watch very carefully, and I'm just going to highlight where you must watch. Watch the movement of the coil. Watch the movement of the magnet and the deflection of the needle. As the magnet goes into the coil, look, there's no battery here. There's no battery. This is a voltmeter that's centered at 0, which we sometimes call a galvanometer. Okay, galvanometer at least, galvanometer, and we're showing that it can go positive and it can go negative, depending on the direction that that magnet is moving. Now, you could have the magnet stationary and you could move the coil backwards and forwards over on top of it. It doesn't mean that the magnet always has to move. It's about relative motion. And if we move, they need to move, relative motion, sorry, I didn't spell it. They need to move relative to one another. The magnet could be fixed and the coil could move around it, or the coil can be fixed and the magnet can move in it, in and out. Okay, now notice that when the speed of the magnet, this is the other thing. If the magnet moved faster, the quicker it moves in, the bigger the deflection. And now Faraday had to explain this, or scientists had to explain it. And so what we recognize is by doing some experiments, what they recognize is this reading on the voltmeter we called induced. It wasn't there to start, so it was an induced EMF. An EMF is maximum potential. So we call it induced EMF. Okay? And what we're saying is the induced EMF, if there is a closed circuit, then there will be an induced current. Now, to change the current, you could change the speed of the movement of the magnets relative to the conductor. So I've explained that. You could also change the magnitude of the change in magnetic flux. Whoa, 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 whoa. What change in magnetic flux? What is this all about? Let's try and explain that. The last one, we'll come back to this one now, the number of turns in the solenoid. So if we increase the number of turns, we get a bigger EMF. So there's something that we've got here that's change in magnetic flux. Hey, don't get me tied up with big words. Let me try and explain them to you. I just want to recognize one thing. The direction of the induced current can be determined by the right-hand rule. Now, we'll come back to that point as well. But what's this idea of magnetic flux? So magnetic flux, I'm just going to draw it over here, is given this fancy symbol, phi. Okay? It's a Greek letter, and it's not pi, but it's phi. So I know we had Pi Day a little while ago in March, but we've now got phi. Phi, the magnetic flux, is given by this. It's the perpendicular magnetic field times the area. Okay? It's the strength of the magnetic field perpendicular to an area. It's the perpendicular component of a magnetic field times its area, the area through which it passes. So let's just be very clear about this. So if you remember, I said to you earlier on, I drew a nice diagram, well, this diagram here. What we've got here is field lines, and perpendicular to these field lines, we've got an area. Okay? If we keep the area, and we change the area, we take area by magnetic field, the strength of the magnetic field, all those magnetic field lines are perpendicular to that area. The field lines represent the B, and the border represents the A. If we multiply the strength of the magnetic field by the area, we get that thing that we're talking about, phi, magnetic flux. Now, how can we change the magnetic flux? Well, let's just make very sure that we've got this, and we've got it very clearly. First thing, we said the magnitude of the change in magnetic flux. So, guys, here is what Faraday found. If we've got magnetic flux, just from a magnet, there's an area through which those field lines work. And what we've got to do is, as we move them into the coil, they cut across the coil. And we only want the ones that are cutting at 90 degrees across the coil. If the coil has very few, then if they're all the same and they don't, then there's no change. If we just have a magnet inside the coil, no change. But if we move it, we change the movement, then we're changing those magnetic field lines. The area that those cut through and intersect with the coil becomes bigger or smaller depending on the motion. And so that's the idea that we've got. As we move the magnet in and out, we are changing the magnetic flux. How can we cause the change to occur? Well, we can use two things. We can change the area. In other words, make a different sized coil. We can also use a different magnet, bigger magnet. All of those things are possible. So in your notes, it will go through this idea that the magnetic flux is the product of the perpendicular component of the magnetic field B and the area. There's the formula. And if we're looking at perpendicular, we use this cos theta as a way of working out the angle between the magnetic field and the area. If we've got the angle between them, we can work it out. I want to move on because I want to define Faraday's law. So what did Faraday say? Faraday's law of electromagnetic induction states that when a magnetic field moves relative to a conductor, so like a coil, an EMF is induced in the conductor or across the ends of the conductor. Guys, if that's not a closed circuit, there will still be an EMF there. Okay, there will be an EMF there. When there's a closed circuit in the coil, then current is induced in that circuit. Very important difference to note. What we're saying is the induced EMF in the coil is directly proportional to the rate of change of magnetic flux. So there's some important things here, and we are recording them in the equation. This E symbol stands for induced EMF. Okay? The N stands for number of turns of coils. The phi is B times A times cos theta, where theta is the angle between those. And delta T stands for the change in time. Now, that's a mean equation, but it's not that difficult. Don't get a panic. It's really easy because they will give you most of those readings, most of those values. Okay? So don't panic about it. Read the questions and we'll see if we've got time to do one or two. Just remember the principle. As we're moving the magnet, the field cutting across the coil is changing. That area is changing, so there's a change in magnetic flux. If the magnet isn't moving or the coil isn't moving, there's no change, there'll be no EMF. The bigger the magnetic flux is, the bigger the EMF will be, the quicker you do it. In other words, the smaller the time, the bigger the answer is going to be. The more the number of turns, the bigger the answer is going to be. Last thing I want to just go back to is you can determine, it said on the previous page, the direction of the current by using the right-hand rule. Now, I want to just show that to you. And it's difficult to show it when it's moving, but just very carefully, here is the rule. What we recognize when we put the north pole in, when the north goes in, so north goes in, then this end of the bar magnet will become north as well. Okay? They will want to repel each other. As the north moves in, the magnetic field around here wants to be a north pole. So we would recognize, use the right-hand rule to say this end, the current must be going in this direction. Well, let's just get it. The current must be going in that direction because that end would then be north. As I pull it out, this end must oppose the action. So as you put it in, it wants to push it out. As you pull it out, it wants to pull it back in. So this end must then be south, and it wants to attract it. The current will be in the opposite direction. And that's why the needle flicks backwards and forwards. Now, Abram, are there any questions on the page? Any
Yes.
people wanting some help before I get to our question? Because I think, you know what, we've almost run out of time.
Okay, for now, I think you can just take that question and I'll give you one question from the mindsetters.
Okay.
A quick one.
Quick one?
Yeah.
You're going to give it to me now?
I'll give you after that.
Okay, right. So let's make sure that we've got this. Guys, if we want to make the induced EMF bigger, then what you need to do is, it depends on the area covered by the magnet, the strength of the magnetic field, the rate of change, and the number of turns. Now, the questions were quite straightforward, and most of them we've actually already answered, and I want to just mention that. So we've stated the law. Guys, this often comes up in the exam, so please learn it. Don't just forget it. Don't just depend on the equation, learn it.
Here's a question.
Yeah.
Here's a question from two mindsetters saying, what is the magnetic flux?
Okay, I've explained magnetic flux. I'll explain it one more time. Magnetic flux, phi, is the strength of the magnetic field times the area through which it passes, but they've got to be at 90 degrees, so we use cos theta for that. Or we can say it's the perpendicular component passing through an area. If you haven't got the idea of magnetic field, go back, or magnetic flux at least, go back and look at that diagram I drew with the magnetic field lines with the crosses and dots and a box around them. It's that area. Okay. Thanks, Abram.
Thank you very much, John. It's been a great show. I've really, really learned a lot. So are the mindsetters at home.
That's great. It's always a pleasure to be here, and I'd see you again. Work hard.
Right. Thank you very much, Mindsetters. Remember, you can also still send us your questions on our Facebook page or email us at helpdesk@learnextra.co.za. Otherwise, it's been a really, really great show, and I love the spirit of Mindsetters who are helping one another on the page. That's why we like team spirit, and see you on Thursday or Friday or Saturday at the Career Exhibition, feature at the Education Show, 25th to the 27th, Coca-Cola Dome. Right. Bye.
He taught himself to read and write.
Wow, very interesting.
Okay, so here's a guy that came from absolute poverty.
If I may ask,
yeah,
is the Faraday taxi rank named after him?
might be. He's a very famous guy, and his fame has spread all over the world. So Michael Faraday comes from a poor background. He couldn't read or write even up to the age of 11 or 12. Didn't go to school. Taught himself to read or write. Became a lab assistant. In those years, okay, 1780, 1790, somewhere around there, what happened is that only the people that were from royalty could go to university. Only they could be scientists, the nobility. So if you weren't born into noble, you couldn't study science. And you know what? The other interesting about Michael Faraday is he popularized science. He started to explain principles of science to ordinary people. Isn't that amazing?
So amazing.
So I mean, he's got lots of inspiration. Guys, I'd like you to do something, just as a fun exercise. See if you can find out about Michael Faraday. And perhaps even post them on the page.
I'm on it too.
Okay,
You know what?
great.
I'm so inspired.
Let's he's an inspiring man. He's actually got so many things that he found out and he invented, and we can just be grateful to Michael Faraday for not keeping all his knowledge to himself, but by sharing it and making us excited about science.
But we're saying to the mindsetters they should read.
Yeah, read, find out about it. And you know what? He never gave up. Even though he didn't let his background be an excuse for determining where he would get to. And he actually became a very famous scientist just because he was determined. And so the same applies to you. You don't think that because you were born in a poor background, from a poor family, you don't go to a good school, that you can't achieve. You can achieve if you stick at it. So that's my inspirational bit for today. Let's get on with the science.
I'm pumped up already.
Okay, right, guys. Now, let's get going. So what's this thing called the magnetic field? Now, I'm going to take you back to some stuff that I'm sure you've done in primary school. Do you remember when you dealt with magnets? So I'm just going to extend this page a little bit. And I'm going to just do a little drawing here. And hopefully we can get something colored in it. So there we go. We've got a little block over here. And we're going to say, let's make that side the north, and let's make that side the south. And we've got a little magnet, a bar magnet. Now, what do we know happens around a bar magnet?
Secondly, follow us on Twitter at LearnExtra. And lastly, you can download the notes. They're already posted on our Facebook page, all for free on learnextra.co.za/live. And let's learn, have fun also.
Abram, thank you so much. Right, now guys, let's get going. So, electromagnetism. So what are we going to do today? There are a couple of things we're going to look at. The first thing that we're going to look at is we're going to discuss the magnetic effect. So let's just get the pen right. The magnetic effect of an electric current. So we're going to look at what happens when current passes through a current carrying conductor. And we'll be surprised, or we shouldn't be surprised because you've seen it before, that there's a way of, if you allow current to pass through a current carrying conductor, it produces a magnetic field. But then the exciting bit is that we're going to go the other way. So we're not only going to say, well, if a current produces a magnetic field, we're going to say, what can we do with a magnetic field to produce a current? And that's revolutionary. It actually transformed the whole of human history. We would not be in the position where we are today if it wasn't for this understanding that you can take a magnetic field and you can make current from it. Because if we were just dependent on batteries, we'd have a whole lot of lemons and metal stuck into them and have cells like that. We wouldn't have all the electrical appliances that we've got. We wouldn't have dynamos and motors and generators, and I know the grade 12s are going to be learning about that a little later as well. So guys, this is important. This is foundational stuff. You need to appreciate and understand that you can both produce a magnetic field from a current, but you can use a magnetic field to make a current, to make a potential difference. And we talk about that as electromagnetic induction. And the amazing man that discovered all about this process is called Faraday. Michael Faraday. He's one of my heroes. Abram, did you know that Michael Faraday, although he lived a long time ago, has got so many things that we can learn from him. He didn't have a formal education, so he was basically kicked out of the house because his mom and dad couldn't look after him at the age of 11.
Sure.
Between 9 and 11, okay? And he had to start working. So he was an unemployed youth, okay? And he went and he got a job as a bookbinder. At that stage, he hadn't been to school.
Wow. Hello, pre-matriculants. I hope you're up
Not
and ready now.
matriculants.
It's pre-matriculants.
Pre-matriculants.
That's what I just
sorry.
said. That's
Hey,
what I just said,
you're
John.
too sharp today.
You
Sorry,
know what, John
Abram.
is up and ready.
Yeah, I'm wanting to jump in, hey? Yeah.
I see.
Yeah.
Okay, once more again, good afternoon to you all pre-matriculants. Hope you're up and ready to learn more with us. As you can see, John is up and ready. I cannot say anything. John, how's you?
I'm really good, thank you. Great to see you again, grade 11s. Now, last night, I just did a little bit of a thing with some of the people watching maths, but today I've got the whole show, so we're going to do the whole thing. So let's get going.
Right, talking about what we're doing today. What's on the menu?
It's electromagnetism. So it's the connection between electricity and magnetism. Now, you might have played with some magnets. We all know about electricity, the lights, and what have you. Now we're going to see how they work together, how we can put those two ideas of electricity and magnetism together. Isn't that cool?
It's so cool. You know what? 2 words to describe the show. It's just fun and learn.
Absolutely.
That's all. I'm looking forward. Well, mindset is to join us on this fun and learning show. Make sure that you go over Facebook. Our Facebook page is facebook.com/learnextra.